doing great. So today we have two talks on different realization of dark matter, heavy dark matter. And our first speaker is Nicholas Orlofsky, and he will tell us about Electroweak dark monopoles from preheating.
So thank you for inviting me to speak, and of course thank you for organizing this series so we can all continue to stay connected. So today I'm going to be talking about this paper with Yang Bai, who is of course speaking right after me on some other works somewhat related, and his graduate student Mrinal Karwar. So the motivation for this is a somewhat simple question, which is, can you have some regions or some pockets of the universe where there's a different electroweak BEV than the ordinary one that we're accustomed to? Maybe even some pockets where you have complete electroweak symmetry restoration. And of course, since I'm talking to you, the answer is yes. And what I'm going to tell you about is that you can do this with a dark sector that has only two ingredients. And the first ingredient is some dark monopole in the dark sector, or some other topological defect, but here I'll focus on monopoles. And the second thing is some Higgs protocoupling between the dark and the visible sectors. So with that motivation in mind, let me just outline what I'll be discussing. So first, I'll give a brief review of what the HOOFT-POLYAKOV monopole is, and then after that, I'll include some Higgs protocoupling to the dark sector and show how this leads to some modified electroweak BEV inside of the dark monopoles. After that, I'll talk about how you produce these. So first, I'll review how monopoles can be produced in thermal phase transitions. And as we'll see, maybe contrary to what your intuition may say, you end up actually underproducing them by thermal phase transitions for the ones that are phenomenologically interesting for us. And so I'll also discuss how you can produce them during preheating, and how you can make more of them during preheating. And finally, I'll talk about some of the phenomenology, how you would detect these in the detector, and what sorts of signals they give. Okay, so starting with HOOFT-POLYAKOV monopole, we'll consider the simplest example here, though you could of course write down a more general. You could write down some other gauge symmetry breaking, but the simplest one is just SU2 breaking to U1 via a triplet dark Higgs scalar that we call phi. And so you have in the Lagrangian the normal kinetic terms and gauge coupling, and then also some spontaneous symmetry breaking potential term for the dark Higgs. Then, if you write down these fields in the so-called hedgehog gauge, where the gauge index is related to the spatial index, then you can write down the time-independent equations of motion for these two fields, where I've rescaled these, taking out some dependence on F and done some rescaling here. And so you get these two equations of motion for the dark Higgs and for the dark gauge fields. And you want to solve these with the following boundary conditions. You of course want at infinity that the dark gauge symmetry is completely broken, so phi equals to 1, and u equals to 0 corresponding to just some ordinary monopole like B field. But then at the origin, you want that the dark gauge symmetry is restored, and also you have this requirement on U from needing a finiteness of the solution from this equation of motion. And you can see that in these equations of motion, there's after doing this rescaling, there's only one important parameter for the whole thing, which is this the quartic coupling lambda divided by the dark gauge coupling G squared. Okay, so once you have that, you can go ahead and compute the solution. And so here it is for two different values of this lambda on G squared. And so you can see that in general, the profile for U, which was the dark gauge field, is not very dependent on this parameter, but the profile for phi is somewhat dependent on it. So for lambda on g squared less than of order 1, then the profile for phi has a similar radius to the profile for the gauge field. Whereas if you take this much larger, then the profile becomes much smaller than the gauge field profile. So the two important quantities for determining the radius of the phi profile, which is the one that is most important for us, are the mass of the dark gauge field in W prime and in H prime. So put succinctly, the radius of the phi profile is just essentially given by the minimum, something of order the minimum of the inverse of these two masses. Okay, you can also go ahead and calculate the monopole mass, and you can do this integration for all the field energies, and you end up getting this expression for pi f on g times some integration factor, which varies between 1 and 1.8, depending on the value of this lambda on g squared. Okay, so that pretty much wraps up what I want to talk about with just ordinary HOOFT-POLYAKOV monopoles. The one thing, though, that I do want to point out is that both of these go, if I set that lambda is smaller or of order g squared, then both the mass and the radius end up going as g inverse. And so that means that if I make both g and lambda suitably small, then both the radius and mass can become somewhat large, and in fact even macroscopically large. And so that'll be important later on when we want to talk about being able to detect these pockets of modified electroweak properties. That we want to have monopoles that are large enough radius that we can actually see that they're there. Okay, so now that we know a little bit about monopoles, let's add a Higgs portal to our dark monopole. So we'll now give this potential for the dark Higgs phi and the standard model Higgs doublet H, and we have some Higgs portal coupling, this lambda phi H term that couples these two together. You get VEVs for the fields given by these expressions, and the thing that I want you to see here is that I've made maybe a somewhat unusual looking choice for the sign of mu h squared. I've chosen it to be positive as opposed to negative, as we normally would. And so here the symmetry breaking for this particular sign choice is such that the VEV for the phi field drives the Higgs field to its non-zero VEV. So this is important because we know for the monopole that in the interior of the monopole, phi actually goes to 0. And so that means that we expect that in the interior of the monopole for this case, when phi equals to 0, the Higgs symmetry is completely restored, and you can have H also equal to 0 inside the monopole. But outside the monopole, phi of course goes to its VEV F. And so outside we recover the usual electroweak VEV. Okay, so that's just one of the possible sign choices that you could make. There are actually several different choices that one could make that allows for both of these fields to have non-zero VEVs. The first one is just all of these couplings positive, and that's case 1. The other cases don't allow for a complete symmetry restoration, but they do allow for some change to the electroweak VEV that could still be an order 1 change to the electroweak VEV. And so for 2 of them they allow it to be smaller, and for 1 of them it increases the VEV. And most of these come down to these 2 signs of the mu h squared and of the Higgs portal lambda phi h coupling. Okay. So now let's go ahead and again solve the equations of motion. So we have these previous equations that I showed you before, and we can go ahead and add in the new terms to account for this for the Higgs portal coupling. And so you have some dependence on the Higgs portal coupling for the phi and u fields, but mostly the new thing is the equation for the Higgs. And the other important thing is that you have this new boundary condition, and you'll see that the boundary condition for the Higgs is actually a little bit different. It's Neumann as opposed to Dirichlet. And so that again comes from wanting the terms to all be finite as r goes to 0, particularly the first derivative term on the left-hand side. And so that means that, of course, the Higgs can take on any value from 0 to infinity at r equals to 0, as opposed to the other fields that have fixed values. Okay, so then we can go ahead and again solve these equations. And here's what you get for a few of the cases. So let's focus on the left side for the moment. So all of these plots have the same, the first three parameters are the same, f, g, and mh prime. So that sets both the gauge boson, dark gauge boson W prime mass, and the dark Higgs boson mass to 1 GeV, just in this example. But what that means is that the characteristic radius of the monopole, even before I look at the Higgs field, is going to be something that's of order an inverse GeV, which is much larger than the Electroweak scale, which is 10 to the minus 2 inverse GeV. So here you can of course see the solution is exactly what we expect. Once we get to the inside of the monopole, there's some critical radius for which the Higgs becomes completely 0, and the Electroweak symmetry is completely restored. And then the difference between the solid and dashed lines are just varying the Higgs portal coupling lambda phi h to just show what sort of the dependence is there. And here I should mention that the Higgs Vev and the Higgs standard model Higgs mass are both fixed to the standard model values. Okay, so there is some dependence on this lambda phi h. Of course, you could imagine turning up lambda phi h to be quite large, in fact, and you could imagine that you could have even some fine tuning between these two terms to make some very, very large radius. We're not going to consider that here. We'll keep these terms comparable to each other so that we don't have some fine tuned cancellation between these terms. And then on the right hand side is just these other cases where the Higgs is not completely restored, but you have some still order 1 level modifications to the Vev in the interior of the monopole. Okay, so much for the Higgs portal coupling. So now that we've seen that we can have these interesting monopoles that can have changes to the Electroweak properties, and also have large radii greater than the Electroweak scale, let's talk about how you produce them. Okay, so your intuition, maybe when I talk about monopoles, that you may think of initially gut monopoles, and you may think, okay, well, you have this gut monopole problem where you overproduce them, and you need something like inflation to solve them, to get rid of them and solve this problem if they exist. It turns out that while that's true for gut monopoles, for the monopoles that we're considering where we want to have some somewhat large radius, thermal phase transitions tend to underproduce them, and this must come down to the monopole anti-monopole annihilations after the thermal phase transition. So let me briefly review this story. After a thermal phase transition, the spontaneous symmetry breaking essentially chooses different symmetry breaking phases and different patches of the universe, and so here's just a toy example for U1 with different directions. And at the points where these different coherent regions meet, there may be some topologically impossible, essentially, to resolve these all to the same to the same symmetry breaking phase. And so you end up with topological defects, in this case, monopoles. Or I guess in the case of the picture, it would be strings, but for us, we're talking about monopoles. And so the monopole number density can be fairly simply computed as just the correlation length of these domains to the -3 power. And then we have some, we know that this correlation length has to be less than the Hubble horizon at the time that the phase transition occurs. So that's what's traditionally known as the KIBBLE limit for the monopole number density. So this sets a lower limit on the monopole number density given the phase transition. You can get a bit more sophisticated and really delve into the details of what happens in a first or a second order phase transition. It turns out that this isn't so important because afterwards there may be a period of annihilations that ends up setting the density. So I'm not going to dwell too much on all of these details. It was worked out early on by these folks. And the main thing here is just to say that you can produce enough in a phase transition to where annihilations become important, especially in a second order phase transition where the number density is quite enhanced compared to the first order phase transition. Okay, so let's then talk about the more important part, which is annihilations. So after monopoles are formed, they're sitting around in this thermal plasma, thermal charged plasma, and they're bumping into all these, say, dark gauge bosons, the W plus minus that are charged under the same under the dark gauge group. And as a result, they undergo this random motion. But if you have two of them close enough together, through all this jostling around, they can develop some drift velocity towards each other. And so while this thermal phase transition is present, monopoles, nearby monopoles are able to find each other, form bound states, and eventually annihilate. But once the thermal charged plasma goes away, say once the temperature goes below the mass of the particles that are in the plasma and the plasma itself annihilates, then the monopoles are able to free stream. They don't often find each other. They don't often annihilate, and the annihilations essentially freeze out, giving some leftover relic density. Not too dissimilar, I guess, from what we think of for WIMP freeze out. So you can work out all the details of this, and feel free to ask. I have some backup slides if you'd like. But the result was worked out by Preskel in '79, and depends on this parameter kappa, which is the ratio of the dark and the visible sector temperatures. But most importantly, depends on this product of G times F squared. And so, as promised, is independent of the initial abundance as long as you've produced enough in the initial phase transition. It's only dependent on the details of the annihilation. But you'll recognize G times F is, of course, the W prime boson mass, which we know set the radius of our monopoles. And so what this means is that if we want our monopoles to be a sizable fraction or all of the dark matter, then our radius must be very small compared to the electroweak scale, with 1 on V. And so what we'd like to do is try and figure out, is there another way to produce monopoles with a large radius that can produce more of them than what's produced during a phase transition. And also, as an aside, I'll just mention, of course, it's now clear from this that if you put in a gut scale for F 10 to the 16 GeV and you keep G of order 1, then you still recover the gut monopole problem that you're familiar with, where you would vastly overproduce them.
So sorry, may I ask a question?
Yeah, sure.
Interrupt. So you said that it doesn't depend on the kind of phase transition that you have, the abundance, or?
Right. So the initial abundance certainly does depend on it, but all I'm saying is if you have enough of an abundance to where annihilations become important, then the details of the abundance that you get at the phase transition doesn't end up determining anything for the relic abundance today.
Okay, but this you would not expect for a gut monopole, this to happen, for instance.
Sorry, what do you mean you don't expect it?
No, I mean, this mechanism that is efficient, you would expect also for a gut monopole?
Yes. Yes, if I remember correctly, then yes, there is some annihilations that you still have to take into account for even the gut monopole. But as I said, also the second order phase transition produces more than the first order phase transition. So there is like some details to be worked out there. I don't want to say that it's completely unimportant. Just that for our discussion, this ends up being the limiting factor for what our dark monopoles can.
Thanks.
Okay. Okay. So let me very briefly talk about how you can get monopoles via preheating. So the idea is you have your inflaton oscillating in, say, a quadratic potential, and it's coupled via this lambda I phi to your dark Higgs. And if you write out the equations of motion, so let's see. So first, initially, you suppose that the dark Higgs has already has its symmetry broken before the end of inflation. So it's uniform everywhere. It uniformly takes on the same phase, which I just take to be in the direction of pi1. And then you can write out the equations of motion for the fluctuations about this about the VEV. And here I'm working in Cartesian coordinates, so phi1 plus phi2 plus phi3. And so if you just get the linearized equations of motion, they end up being in this form of the Mathieu equation. And here's all these various parameters. It's not too important for the purpose of this talk to see what all these parameters are. I just put them here for completeness. But the main thing to know is that the Mathieu equation has these bands of instability where you have some exponential solutions to this equation. So where the solution goes is e to the mu, which is some instability parameter times z. And here this is the stable instability region plot in terms of A and Q. And we tend to live on or above this A equals to 2Q line, just based on the parameters that I had on the previous slide. And as the universe evolves, as the scale factor increases, you move further and further down, going through all these various instability bands. So this process ends up selecting some preferred K mode that gets more enhanced than all the other K modes. Essentially, the one that is enhanced the longest gets the most enhanced, because there's just an exponential difference between one that is enhanced from the very beginning of preheating versus one that is enhanced starting in the middle of preheating. And so you get on the right-hand plot for K near this this preferred mode K star, you get some very large exponential growth. If you vary K away from this K star, then you still get some growth, but it's still many orders of magnitude smaller. And also, if you make your mode massive as opposed to massless, then the growth is also suppressed. And so what you should have, so what the picture of this should be in your mind is that you start at the very bottom of this potential, and the fluctuations in the radial direction are suppressed, but the fluctuations in the phase direction or the axial direction in this picture start to grow. And if you allow them to grow for long enough, then they can start to explore the whole range of this all of the symmetry breaking phases of your theory. And so that's exactly what you need for monopole production, because if you have one patch that has a symmetry breaking phase over here and another one that's on the opposite side of the potential, that's how you end up getting monopoles, just like for the thermal phase transition. And so So then you end up just getting some modest requirements on essentially how long the parametric resonance is in order to have monopole production. So then you can just ask, okay, what is the number density that you get of monopoles at the end of this? So just like for the thermal phase transition, it ends up being going as some correlation length to the -3 power, and then you just have to ask what is that correlation length for preheating. So that correlation length should be directly related to these K modes, these K star, and K star itself I haven't told you yet, but it is essentially related to the frequency of the so the mass of the inflaton with some weak dependence on Q naught. Okay, so then at the end of it, you get this abundance, and this depends on the depends on this ratio of the lambda phi and the gauge coupling G, but no longer depends on the radius. So so the upshot of all this is that now we can produce monopoles of a lot of different radii, being most or all of dark matter. Okay, so so you need to take into account what some of the constraints are on this, of course. And when you do that, you end up getting all of this shaded region where you can produce monopoles, making up all of dark matter. The difference between the 3 different colors is not so important for this talk. I just flash up here what it is. It has to do with whether the dark sector is in chemical and kinetic equilibrium or not. But for the purposes of this talk, just all of this region is allowed. And so you can compare this against the purple dashed line, this KIBBLE-ZUREK plus annihilation line. And if you do a thermal phase transition, then you have to sit on this line, so at very small radius, as we reviewed. But now with preheating, you're able to go to a much larger radius than what you expected from a thermal phase transition. I'll briefly mention also, I have this line f equals 10 to the 5. There's no actual constraint here. Actually, so far, I haven't even invoked in this whole production story anything about the Higgs protocoupling. But if you actually want a Electroweak-Symmetric monopole, then there is some constraint, because we also want our dark sector to be decoupled from the visible sector so that we don't run afoul of dark radiation constraints, delta and effective constraints. And so again, in order to avoid some fine tuning between the 2 terms that set the Higgs VEV, you end up wanting to sit below this line of f equals 10 to the 5. So you want to be greater than f equals 10 to the 5. If you want, again, only if you're interested specifically in making Electroweak-Symmetric monopoles.
So you have 5 minutes.
Okay, thank you. That's perfect. So let me now move on and talk a bit about how you look for these, what sorts of signatures they give in detectors. So for this section here, I'll just focus on Electroweak-Symmetric monopoles. You can look at our paper for a little more details of other cases. But okay, so going with that, for this calculation, let's just take a simple approximation and say that the potential of a nucleon passing through the Electroweak-Symmetric core of a monopole looks like a spherical well. So when the nucleon is inside the monopole, it's massless, feels less potential from the Higgs, and so has this sort of square well sort of potential. And so then you can calculate the elastic scattering cross section just using the Born approximation. And when you go through this integration, you end up getting that the cross section goes as this radius to the 6th power, and also has and for this choice of radius, which is even a bit less than the Electroweak scale, already you can see that you're going to be able to detect this with modern direct detection experiments. Of course, it can't grow as the radius to the 6th forever. It has to at some point saturate to the geometric cross section. And so here, yes. Okay, and so here, so here we just take some cutoff between these two, going smoothly from r to the 6 to r squared. There is some other interesting phenomenology that happens here. Besides elastic scattering cross-section, you can also have things like bound state formation, where nuclei, because they're massless inside the monopoles, tend to want to stay there and can radiatively capture onto monopoles. I'm not going to talk about that so much here, but stick around for Yang's talk, and he'll describe some of this. Okay, so then that brings me to the constraint plot that we can make. So in the red shaded region is the constraints from xenon 1 ton. And this little kink at the bottom here, where it changes slope, is just the change from the r to the 6 behavior from the Born approximation to the geometric cross section r squared. The maximum mass is of course set by having a large enough flux that you have monopoles passing through your detector during the time of the experiment. The purple shaded region shows where you get tracks in ancient mica. So this is looking at rocks that have been sitting in the earth for a long time, and seeing if you see any tracks of monopoles or other particles passing through them. And you can see already that these two shaded regions are starting to impinge upon this. Sorry, did I hear a question?
Go ahead.
Okay. Already starting to impinge upon this region that we've shown for where parametric resonance can produce monopoles. Now I've cut off the xenon 1 ton constraint at this horizontal line because that's where you start to get multiple hits in your detector. So rather than just hitting one nuclei on its way through the detector, it hits actually multiple nuclei and leaves a trail as it goes through. And so this would require reanalyzing it, kind of doing reanalyzation of the xenon 1 ton data. But we think that if you do this, you can search for monopoles all the way up to this black line, which is the atmospheric and Earth overburden line, where monopoles are no longer able to reach your detector. Also shown, of course, is this this decoupling limit, f equals 10 to the 5 GeV, and also constraints from H to invisible to case. Okay, so with that, let me just go ahead and wrap up. Here's my summary. I hope that you take home three messages from this talk. The first is that if you have a dark sector with dark monopoles and a Higgs portal coupling, then you should always expect that inside of your dark monopoles, you have some change in the electroweak symmetry, and maybe even electroweak symmetry restoration, depending on exactly the parameters of that theory. Secondly, you can produce these during thermal phase transitions, but of course, you end up underproducing them. They end up being a very small fraction of dark matter. But if you consider other production mechanisms like preheating, then you can expand the possible radii for which these can be produced with large abundance, comparable to dark matter abundance. And finally, you can look for these in large volume terrestrial experiments and look for interesting signals like single and multi-hit, and other things that Yang will talk about in the next talk. So thank you for your attention.
Thank you very much, Nicholas. So we have time for a couple of questions. So either in the chat or just speak up.
Oh, hi, Nicholas. This is David. Can you hear me?
Yeah.
Yeah, I can hear you anyway.
Oh, hi.
Okay.
Hi. So thanks for the talk. Really cool. I appreciate a good money plot, and these are very nice money plots. So I wanted to ask you, your kind of main plot number 2, if I understand the sort of logic correctly, you're basically saying, let me be the most generous with regards to a possible preheating scenario, and then this could be populated.
Yes.
If I were to go the other route and consider the sort of minimal thermal production during the electric phase transition, and I were to say, let's assume no preheating,
Yes.
what would the equivalent of plot number? So presumably the direct detection in plot 3 would stay the same.
Yeah, good.
Right.
Okay,
so what are the areas in plot number 2?
Yeah. So this is what happens when you take the abundance as going as being determined exclusively by the thermal phase transition. So here I have the dark matter abundance 1. Here is 10 to the minus 10. So you can see that actually, in principle, you can constrain with xenon 1 ton plus some other low mass dark matter experiments. You can actually constrain this as a very small fraction. The caveat, though, is that you can see this is already to the left of the f equals 10 to the 5 line, which is the one that kind of was giving you the where you needed to be below for decoupling of the dark sector from the visible sector. So this region is already excluded, unfortunately, and you can scan this parameter to see if there's any if there's any place where xenon 1 ton can exclude things that that aren't excluded by the decoupling. There's not. It comes pretty close, but there's just not quite any place that it does. And so yeah, you would need some sort of significantly longer running or larger detector to hope to look for the small fraction. Thanks for the question. So I could show that slide.
Okay, so I see KIBBLE-ZUREK is raising his hand. So
yes, could you tell me how you estimated Y, H, and N Higgs nucleon coupling?
Good. So yeah, so here this is just the from the coupling of the Higgs to the nucleon, just ordinary direct detection cross section. Assuming that looks something like the Higgs mediated coupling to dark matter.
But that is part of the one. But what's happening here is more drastic. The inside monopole Higgs wave vanish. Can we cite part of the picture here?
Right. So it's not enough just to let's see. Actually, I think I have a backup slide. Not enough just to consider like a T-channel Higgs being emitted. So you can. This is a calculation for the case where the symmetry is not completely restored, but gives a little bit more details. So you can see the how the mass changes as a function of the sorry, this is for Higgs to monopole. But yeah, I mean, this kind of gives the general idea that you vary the Higgs mass as a function of the VEV, and you can get the coupling of the Higgs to the monopole, and then get the and then yeah, so then that multiplies by the this YHNN, which again is just treating it as a Higgs, essentially through a T-mediated exchange with the nucleon.
The picture is that they couple nucleon monopole couple via the Higgs exchange, rather than the picture where the nucleon get into the monopole and something drastic happens. Okay, thank you.
Okay, very good. So I think we need to move to next talk. Thank you very much.